In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a musician, a scientist, a man with a flute. Remember, in this universe of wonder and mystery, sometimes the most unlikely heroes make the biggest impact. Keep your mind open, your heart brave, and who knows, you might just find the ether within yourself. So here's to Dayton Miller, the flute ether master. His melody still resonates, a testament to the power of harmony in a chaotic world. In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium.
Thanks for being here, and if you're already listening in on Ether Cosmology, sorry for the redundancy here, but this is reading and research night, and I'll put this out there for the third time now that we have changed our schedule up. So Tuesday nights is presentations and or open discussions here on the Discord server, and then on Thursdays we will be doing research and reading. We're not just going to read through chapter after chapter of books, but we're going to do like bring your own paper to read, bring a video to watch, bring some research to do type of thing. So that's what we're doing here on Thursday nights now. And thank you for being here with us to do some reading and research with us. And by the way, if you want to join the Discord server, you can head on over to discord.gg/Ether Cosmology. That's spelled with AETHER. Or just go to ethercosmology.com and click on the little Discord icon there on the left side. In any case, thank you everyone for being here one more time. And yeah, so without further ado, let's get into some reading. Did you want to just like pick up reading, Piezo? Are you still there?
Sure. I'll start with the heading.
Yeah, go for it.
Can you bring up your mic a bit, Pizzo?
Yeah. Is that better?
Yeah, it is.
Yeah, now we're talking.
Toroidal Vortices of Light by Chen-Hao Wan, Qian Cao, Jian Chen, Andy Chong, and Ziwen Zhan.
Gesundheit.
Nice.
Toroidal vortices, also known as vortex rings, are whirling closed-loop disturbances that form a characteristic shape in liquids and gases, and propagate in a direction that's perpendicular to the plane of the ring. They are well-studied structures and commonly found in various fluid and gas flow scenarios in nature. For example, in the human heart, underwater air bubbles, and volcanic eruptions. Here we report the experimental observation of a photonic toroidal vortex as a new solution to Maxwell's equations generated by the use of conformal mapping. The resulting light field has a helical phase that twists around a closed loop, leading to an azimuthal local orbital angular momentum density. The preparation of such an intriguing state of light may offer insights for exploring the behavior of toroidal vortices in other disciplines, and find important applications in light-matter interactions, optical manipulation, photonic symmetry and topology, and quantum information. Toroidal vortices, also known as vortex rings, are intriguing propagating ring-shaped structures with whirling disturbances rotating about the ring. Toroidal vortices are not uncommon in nature and science. Indeed, aquarium visitors are often amazed at how dolphins master creating and playing with bubble rings, which are air-filled vortex rings propagating in water. The scientific investigation of vortex rings dates back to 1867, when Lord Kelvin proposed the vortex atom model. After 1.5 centuries, vortex rings are still being actively investigated in a variety of disciplines. For example, in meteorology, vortex rings of wind, rain, and hail are tightly related to the development of microbursts, which pose a great threat to aviation safety. In cardiology, asymmetric redirection of blood flow through the heart resembles a toroidal vortex. In magnetics, the experimental observation of vortex rings in a bulk magnet has only just been accomplished, opening up possibilities for studying complex three-dimensional solitons in bulk magnets. Well, in photonics and light science, there have been studies on toroidal dipole and multipole excitation in metamaterials. However, the theory and experimental demonstrations of a propagating photonic toroidal vortex remain elusive. In this article, we fill this gap based on conformal mapping. Conformal mapping is an angle-preserving transformation that has been utilized to bend optical rays with metamaterials in mapped directions to circumvent hidden objects so as to achieve optical cloaking. Here, we exploit conformal mapping to reshape a photonic vortex tube into a toroidal vortex. The photonic toroidal vortex is an approximate solution to Maxwell's equations and can propagate without distortion in a uniform medium with anomalous group velocity dispersion. The observation of a photonic toroidal vortex, like its counterparts in other disciplines, will open up a wealth of physical mechanisms to explore, such as toroidal electrodynamics, toroidal plasma physics, complex symmetry and topology for light confinement, sensing and manipulation, and interaction of light with metamaterials. The discovery of photonic toroidal vortices may also open up possibilities for the development of novel laser designs, as well as energy and information transfer methods. The electric field of an optical wave packet is expressed as the product of the carrier at the central frequency and envelope function. Under a scalar, paraxial, and narrow bandwidth approximation, the envelope function that describes the dimensionless light field in a uniform medium with anomalous GVD is given by this equation. The second derivative of, I can't remember what that symbol is. You remember
Psi.
psi. The second derivative of psi with respect to x plus the second derivative of psi with respect to y plus the second derivative with psi with respect to tau plus 2i derivative of psi with respect to z equals 0, where psi is the scalar wave function, x and y are the normalized transverse coordinates, tau is the normalized retarded time, and z is the propagation distance. The reason why the envelope function is expressed in a dimensionless way is to conveniently unify the spatial and temporal coordinates and derive a stable solution in the spatiotemporal domain. Anomalous GVD is chosen so as to obtain the same sign for the spatial and temporal second derivatives. As demonstrated by supplementary equation 14, a spatiotemporal Laguerre-Gauss tube with the vortex line directed in the y direction is a solution to equation 1. The iso-intensity surface of a spatiotemporal Laguerre-Gauss tube is labeled at position 0 in figure 1. According to conformal mapping theory, the complex exponential function corresponds to a log polar to Cartesian coordinate transformation. This conformal mapping transforms a line to a circle in two dimensions and performs a tube to toroidal mapping in 3D space. Here we adopt an afocal system that consists of two computer-generated phase masks to perform optical conformal mapping, XY to UV, where XY and UV are the Cartesian coordinates in the planes at which the two phase elements are located. The log polar to Cartesian coordinate transformation requires that U equals B exponent exponentiate. I don't know what that stands for. Negative x over a cosine y over a, and V equals B exponentiate negative x over a sine y over a. The first phase mask performs the mapping from a tube to a toroid, and its phase profile can be derived through stationary phase approximation as phi 1 xy equals kd negative ab exponential. I'm just going to say exp negative x over a cosine y over a minus quantity x squared plus y squared over 2, where k is the wave number, d is the distance between the two phase masks, and a and b are used to adjust the beam size and position in the UV plane. The simulated evolution process for the mapping from a tube to a vortex ring and free space propagation is labeled at positions from 1 to 5 in Figure 1. The second mask recollimates the light. In the time reversal direction, the second phase mask performs a Cartesian to log polar coordinate transformation. Similarly, its phase profile can be derived as the following equation. Now, can we look at the figure? Ooh, yeah. So they're starting with the tube, and they're basically bending it to where the ends meet into a closed loop. Okay, from a spatiotemporal vortex tube to a vortex ring. The spatiotemporal vortex tube acquires phase phi xy and begins the transformation process in free space repropagation. After completion of vortex ring formation, a second phase mask phi 2 UV is applied to collimate the light. The color scale represents the phase of the unwrapped, or the value of the unwrapped phase. Okay, so if you scroll up just a little, they have that tube at 0 on the left, and if you imagine it's just like a cylinder where there's well, it's actually got two little tubes. It's cylinder with like imagine vortexes being in each one of those little two tubes, and then when they connect it, it becomes a closed loop like a donut, and then you get this like spiral around, like it's going around, and it creates a vortex in the center in the second image. Scroll down a little. Right, see how it's going clockwise? That's the direction that it was propagating through the tube, but this creates a vortex through the center of the donut now. Okay. After traveling through the two phase masks, the spatiotemporal vortex tube will be mapped into a photonic toroidal vortex. The toroidal vortex as a solution to equation 1 and the remapped coordinates can be approximately expressed as equation 4. I wonder what negative, I see negative I arctan right there. Well, what's the L? I wonder what the L is for. Negative IL. Interesting. Some abstract mathematics. Where this R function is R naught is the radius of the circular vortex line. L is the integer. I got it. And Z naught is a constant. Figure 2 shows the ISO intensity.
Yeah, the R's are
Wait,
perpendicular.
Figure 2 was this one. Okay.
Shows the ISO intensity surface of a photonic toroidal vortex in different perspective views. The photonic toroidal vortex possesses a 3D phase structure that rotates around a closed loop, forming a ring-shaped vortex line while advancing in the direction perpendicular to the ring orifice at the speed of light. So I think the ring orifice is the hole in the center of the donut. Okay, so there's a ring-shaped vortex line, and the photonic toroidal vortex forms this ring-shaped vortex line, but it advances in a direction perpendicular to the ring orifice. So, in other words, the donut is moving like in a direction, and the direction is in like the direction that, like, if you drew a line through the hole in the center, the direction the line through the hole in the center is pointing. That's the direction that the ring moves.
Nice. Thank you. Good explanation.
In Figure 2, the rotating spatiotemporal spiral phase is represented by colors, and the direction of local orbital angular momentum, OAM, density is marked with arrows. The experimental apparatus begins with a dispersion-managed mode-locked fiber laser that emits a chirped pulse, figure 3. The light from the source splits into a reference pulse and a signal pulse. Okay, so they have a laser beam that's a pulsed laser, and it says that it's mode-locked. I'm not sure what that means. The reference pulse is dechirped to a transform limited pulse through a grating pair. Also, not certain what that means. A reflective mirror is mounted on a precision stage after the grating pair so that the path length difference between the reference pulse and the signal pulse can be controlled accurately. Okay, so they're using this mirror in order to adjust, like fine tune the angle of the mirror in order along with the rest of the devices in this setup, so that they can tune it very finely and control the path length to make this the two paths of equal length. I'm assuming it's kind of like interferometry in a little bit. The signal pulse propagates through a 2D pulse shaper that consists of a grating. Oh, I get it now. The grating. It's like a think of it kind of like a filter, I mean, think of like your vent in your floor that your air comes through. It's got like the cross slits, and so if you imagine the air is flowing through it, then the air is coming out in like little slits now because it went through the grating. It consists of a grating, a cylindrical lens, and a reflective programmable spatial light modulator, SLM1. SLM1 is situated in the spatial frequency temporal frequency plane and applies a controlled spiral phase to the signal pulse. So it adds a spirality to the pulse. After a spatiotemporal Fourier transform, the signal pulse is converted to a wave packet carrying a spatiotemporal vortex. Yeah, so it spirals it and turns it into a vortex. The spatiotemporal vortex pulse then travels through an afocal cylindrical beam expander and stretches in the direction of the vortex line. So then they basically make it wider. SLM2 and SLM3 form an afocal mapping system. So they have 3 spatial light modulators. They are programmed with the phase profiles as given by equation 2 and equation 3 respectively. Parameters A and B are chosen so that the light occupies a great portion of the liquid crystal area. The stretched spatiotemporal vortex pulse transforms into a toroidal vortex pulse through the conformal mapping system. So it appears that they're using, can you scroll up just a little bit? Yeah, right there. Oh no, the paragraph. I don't remember the paragraph. Yeah, okay. It appears that they're using this SLM, right? They've got a grating, a cylindrical shaped lens, and this spatial light modulator. And this spatial light modulator is applying energy to it at such a beat, at such a rate that it adds a applies a spiral phase to the pulse. So it takes this, regular, normal, linear pulse that's sent through the grating and then sent through the cylindrical lens, and it's made cylindrical. So now it's cylindrical, but now that since it's cylindrical and it's like a circle, a cylinder or whatever, now they add the spiral through the cylinder. So you got a spiral in the cylinder, and then they convert it, the pulse into a wave packet carrying a vortex. So this little spiral through the cylinder is creating a vortex, and then this vortex pulse goes through the cylindrical beam expander and stretches in the direction of the vortex line. So I'm assuming they expand it to the size they want it to be, based on like that figure 1 that we saw above, to that little donut ring. And then parameters A and B are chosen so that the light occupies a great portion of the liquid crystal area. I'm not sure what the liquid crystal area is. I need to see the diagram. Can you scroll up to the diagram in figure 4? Or up a little bit more? Maybe it's figure 3. Yeah, here we go. Okay. So they're starting over here at the left with the fiber laser, and then the BS1 splits it to grading and grading pair. See, so it goes to that one and that one, and then that reflects it off. There's a movable mirror over here on the bottom right that helps them to adjust the angle so that they fine tune the path lengths to make sure that there's symmetry. And then on the top, they've got that cylindrical lens and that spatial light modulator at the top, SLM1. That spatial light modulator is what's adding the spirality as it goes through the cylindrical lens. So it's turned into a cylinder with a spiral in it. Bounces off that mirror, goes through another cylindrical lens. So I'm assuming if you get two cylindrical lenses and have it like do a cylindrical transform in two different directions, that looks like there's three of them actually. So they've got like 3-axis cylindrical they're applying a cylindrical geometry on 3 axes, I'm guessing, to make it uh, a toroid.
Interesting.
Okay, so bendy light. Next.
See, and then it's got SLM2 and SLM3. So they've got 3 axes of applying cylindrical geometry to it, 3 axes applying spirality to it with the SLMs, and then it comes out as a toroidal vortex over there where you see at the right toroidal vortex and it's rainbow, and then it goes through BS4 beam splitter 4, uh, and they got the CCD camera. So they've got that short reference pulse. That path on the bottom, remember that path on the bottom is just the original path of the fiber laser. It's not going through any kind of spatial light modulator and any kind of cylindrical lens. It's just the reference pulse. So they're comparing this reference pulse with the transformed toroidal vortex that they've made out of it. So that's interesting. They're actually literally just taking a regular pulse of light, applying a cylindrical transform in 3 axes and adding spiral in 3 axes and turning it into a toroidal vortex. And then when it comes back to the beam splitter 4, which, now that they've got the path length adjusted to equal path length, they can read an interference pattern on the CCD camera between the reference pulse and the vortex. That's pretty cool.
Yeah, it's really interesting.
The toroidal vortex is characterized by interference with the dechirped reference pulse. Yeah.
Actually, that's where they're controlling whether or not you see interference is below to the right of mirror 2, where it says movable mirror. That's where you're literally changing the length of the light path on the right half of this.
Right.
So, yeah, that's how you control whether or not you see interference.
Yeah.
Does anyone know what chirped means? They keep saying that a lot.
Yeah,
No
I'm
idea
not
what-
sure what dechirped
that?
means. It says a chirped pulse from the laser source. I don't really know what chirped means, but
Kind of like, I don't know, a term. I don't want to speculate.
I would guess that there is a lack of squareness to the energy envelope when you're turning your laser on and off using the switching inherent in the laser propagation hardware. You know what I mean? It's the same kind of thing that you're going to see in the DC with reluctance in any kind of inductance in the circuit you've got when you apply a square wave to it, that there's going to be some overrun of the supply voltage while internal impedance sorts itself out at the beginning of the on phase. So I think they're probably just they're just smoothing out the shape, so to speak, back into square.
according to ChatGPT, a chirped pulse in the context of pulsed lasers is a pulse where the frequency or wavelength changes over the duration of the pulse. This can result from dispersion effects, and it leads to a pulse which is temporally broader and has a broader spectral bandwidth.
Oh yeah, okay. So instead of abnormal voltage curve, you have abnormal frequency curve.
Yeah, so
Yeah.
if it starts with a low frequency and ends with a higher frequency, it's said to have a positive chirp. If it starts high and ends low, it's a negative chirp. Chirping is caused by the dispersion of the pulse, uh, which occurs when different frequency components of the pulse travel at different speeds through a medium. This can happen in materials or optical fibers where the refractive index of the fiber depends on the frequency of the light traveling through it. Okay.
Cool.
They can be compensated for in pulse compression techniques. I got it. So like when you got this fiber optic cable, this fiber laser, right? Due to the refractive index properties of the material itself, the the pulse, which has several different frequencies in it, it's like a wave packet, right? The different frequencies will experience different refractive indexes, which will cause them to propagate at slightly different speeds and rates, causing different wavelength and frequency shifts. So when it says a de-chirped reference pulse, I'm assuming that that's where they have eliminated that differential between the frequency components and made it like into like uh, one singular waveform.
One frequency.
Yeah. Okay. To characterize the 3D field information of the toroidal vortex pulse, the transform limited reference pulse is combined with the toroidal vortex pulse by a beam splitter, BS4, that's at the end of the diagram we were looking at, and the interference patterns are recorded by a charged coupled device, CCD, camera. The reference pulse is considerably shorter, about 90 femtoseconds, than the toroidal vortex pulse, which is about 3 picoseconds. So, by the use of a precision stage and a movable mirror, the reference pulse interferes with each temporal slice of the toroidal vortex pulse. By utilizing the characterization method, the amplitude and phase information can be retrieved from the interference patterns. Consequently, the 3D ISO intensity profile of the toroidal vortex pulse can be reconstructed, as shown in Figure 4. That's where they like 3D mapped it. Semi-transparency is applied so that the ring orifice and the hidden ring-shaped vortex core are clearly shown. The outer layer of the ISO surface is colored in purple, and the vortex core surface is colored in red to make the vortex core stand out. Because the phase gradient is dominant in the radial temporal plane, the local OAM density direction is at a tangent to the vortex line,
Bless you.
as indicated by green arrows. Thank you. To present the spiral phase rotating about the vortex core, 3 slices are taken in the radial direction of the ring, as marked numerically 1 through 3. The phase profiles of the 3 slices in local coordinates are reconstructed and shown in Figure 4C. All 3 images show a spiral phase of topological charge 1. The intensity and phase information demonstrate that the generated pulse is indeed a toroidal vortex. The experiment is carried out in air of very weak positive GVD. The topological charge of the photonic toroidal vortex in the radial temporal plane is 1, and the propagation of the photonic toroidal vortex in air over a short distance will introduce only small distortions. More details on the method and data are provided in supplementary figures 3 through 7. In conclusion, we have experimentally demonstrated the generation of a photonic toroidal vortex as a new solution to Maxwell's equations through optical conformal mapping. The preparation of photonic vortex rings is of great importance for studying toroidal electrodynamics, light matter interactions, and photonic symmetry and topology. The concept and conformal mapping method can be readily extended to other spectra such as electron beams, X-rays, and even mechanical waves such as acoustics, hydrodynamics, and aerodynamics, opening up new opportunities for studying vortex rings in a wide range of disciplines. Online content, any methods, additional references, nature research reporting summaries, source data, extended data, supplementary information, acknowledgments, peer review information, details of author contributions, and competing interests and statements of data and code availability are available at the following URL. Okay. Can we go see Figure 4?
Yeah.
Yeah, this one. So, can I see the caption? Oh, there we go. 3-dimensional ISO intensity profile of the photonic toroidal vortex in different views. The maximum intensity set to 1, ISO value is 0.02, meaning that the ISO surface profile includes all points with an intensity larger than 0.02. The spatiotemporal spiral phase is marked with curved, colorful arrows, and the local OAM density is marked with light green arrows. Circulating spiral phase in the radial temporal plane. So that's what it looks like when 3D mapped out.
That's cool.
Yeah, it's like you got the purple, which is like the outside, like the donut itself, but then you have the red, which is the like the vortex inside the vortex.
Kind of like the vector of the whole thing, right?
The core.
Yeah, that's the core, the vortex ring core. Interesting, and it's got if you look close, you can see those arrows are showing which direction it's spinning as it's going, which direction it's helixing in or spiraling in. If you zoom in.
I tell you, man, these Chinese will write just about anything to get out of the country, won't they? It's just fabulous.
Kind
Right.
of, what did you?
They're not afraid to go into the higher level conceptions.
I mean,
What I heard was the possibility to study it more and to to think of it in terms of other disciplines. But what I never saw was use.
well, they
You know what
lasers
I
at the
mean?
beginning.
Oh boy, you can get some bandy light going in your lab too. But yeah, then what? That's the thing that's missing for me here.
Yeah, I think the last paragraph of the first page was talking about potential applications, but it was kind of brief.
Kinda.
Is there like I see that they have a diagram, but is there
The
like
left hand side, the discovery of photonic toroidal vortices. Oh wait, there we go. It will open up a wealth of physical mechanisms to explore toroidal electrodynamics, plasma physics, complex symmetry and topology for light confinement, sensing and manipulation, and interaction of light with metamaterials. The discovery of photonic toroidal
Great.
vortices may also open up possibilities for the development of novel laser designs as well as energy and information transfer methods.
Yeah.
See, here's the
What
thing, the
kind of
information transfer.
information?
Right. Well, if you
Uh,
could encode, think about this. Instead of encoding, because go down to figure 3. You see, oh, yes, yeah, right there. The short reference pulse, bottom right of the diagram. Short reference pulse right there. Up a little bit.
Just short
Yeah,
of
right there.
BS4. Yeah.
Yeah, that's just like a normal waveform, right? And that's how we think of like electricity on a wire, right? We just think of this sinusoidal waveform, and that's
Well,
how we
frankly, that just looks like a transient spike relatively. They're talking about femtoseconds of length for this pulse, for the reference. Just a really high frequency stuff.
Sure, but in general, like if you think of the normal sinusoid of a waveform, that's how we think of, an electrical current or a signal on a wire when we transfer information. If they were able to use this topology, right? Imagine because our internet backbone is encoded with fiber optic sorry, it uses fiber optic cables and the data is encoded through that system through these, sinusoidal waveforms. If they were to modulate it to where you got these three cylindrical lenses and three SLMs and make it 3-axis 3D toroidal vortex pulse instead of your normal sinusoidal pulse, then they could potentially encode various sets of data instead of just a simple 0 or a 1. uh, so it opens up the potential for potentially greater throughput of information transfer, I'm assuming. Because you can encode a lot more information. Like, there's a lot more phase information in the 3D toroidal vortex. You got the direction it's spinning, you got the direction it's spiraling, you got the direction it's rotating, you got the direction it's traveling, you got the intensity at each of those things, the amplitude. I mean, it's there's a lot of information that could be encoded there. I feel like so, and it's
potentially, yeah. I see what you're saying. Or yeah.
am I just dumb or am I not seeing how the ring actually forms?
no, it's okay. We had to
Mostly
figure
through
it
the
out.
cylinders.
So you
They're
see the
actually showing you the modified waveforms in the STOVs that he's pointing at there. That's on its way to being turned into a vortexual shape.
Yeah.
Interesting.
So the cylindrical lenses are applying along, as best as I can tell, applying along each axis a cylindrical transform to an otherwise just normal waveform. So you got the cylinder on the x-axis, cylinder on the y-axis, cylinder on the z-axis. But then you have the three SLMs. The SLMs are applying a spiral into each of those axes. So now you've got it transformed into a toroid after 3 axes of cylindrical transformation and 3 axes of like spiraling. That's what it looks like to me.
Yeah, that's interesting. I guess the only thing I'd want to see is like, do they have? Could you go to the supplemental material, please? They said they have more data. I would just like to see that. I guess maybe it's like an additional attachment.
It's at the URL right there.
Okay. Oh, we don't necessarily have to jump to that. Sorry, I don't mean to derail us.
This is when was this made? Published 2nd June 2022. Wow, this is 2 years old. Received September 2021. Wow, so they did this 3 years ago.
I'll drop this link to the code and stuff.
Julio, thank you.
Juan et
Well,
al.
cool. That pretty much wraps it up for that paper. That was pretty interesting, for sure.
Yeah, they. Can you go down to the left-hand side of that first column real quick again, on the first page? Yeah, scroll down on bottom of the first page. There we go. So they're saying that complex symmetry and topology for light confinement, sensing and manipulation, and interaction of light with meta materials. So the electrodynamics obviously is probably the most important part, right? Like, what's the dynamics behind electromagnetism, but also thinking about using this as a sensing mechanism to scan or look into matter, right? That's very interesting. May perhaps by utilizing this technology they could perfect it in the years to come and find ways to image things at the very small scale better than they do now, because right now we have like tunneling electron microscopy, and it has its limitations, but perhaps this could allow them to peer even further into the fabric of matter, so to speak.
I mean, it's certainly really cool. Yeah. I don't really have a great basis in physics to really understand it that well, but
Oh no, a lot of this is over my head in the terminology of some of these things, but the diagrams help.
Yeah, the diagrams helped a lot on this one, that's for sure.
yeah, definitely.
You guys
Especially with
don't
some of the laser component stuff.
you guys don't automatically interpret cylindrical transformations on 3 axes as a toroid? Come on. Yeah, come on, boys.
Not us mere mortals, Alan. Can you go to the part about the being a novel solution to the Maxwell equations? I think that's kind of key to, at least for me to understand. I'm not sure where that was. If you
What do
control
they
F.
mean by that? Yeah, they don't.
Yeah, approximate solution to the Maxwell equations. It can propagate without distortions in a uniform medium with anomalous group velocity dispersion. So that's really interesting, right? What do they mean by an approximate solution?
Well, the toroid that they measured was not perfectly symmetrical. There's slight perturbances due to its traveling through air and various media, but I'm assuming that they believe that were it a perfect toroidal vortex instead of a slightly imperfect one, that it would be a more exact instead of approximate solution. I don't really know. I can't speak to it because they don't go into much detail about it.
Yeah, that's kind of a really they did not follow up on that statement.
Yeah, that's
Yeah.
kind of a big one. I mean, I'm not trying to be a party pooper. This is cool, but I would like to see the derivation there.
Well, it's
Yeah.
so cool that it brings me to other questions, other macro questions. Like, just imagine if you go scroll right up at the top, see how many authors are in this page. Is it like a dozen people? Oh no,
Five.
five, six people. Just imagine if you had taken this team and put them on the task of like global hunger. Just imagine how things would change so fucking fast with these guys on the job.
Yeah, it's very interesting.
I think part of what I actually think a lot of what they're talking about with the approximations, right? Um they're kind of alluding to it here and talking about when they talk about the dimensionless light field. I think that's why essentially they can remove the dimensions and just approximate it using these derivatives, I believe, is kind of what they're getting at.
The reason why the envelope function is expressed in a dimensionless way is to conveniently unify the spatial and temporal coordinates and derive a stable solution in the spatio-temporal domain, aka 3D space.
And so that's the anomalous GVD. So that is what they were
Group
talking
velocity
about,
dispersion.
yeah. Yep.
Yeah, the group velocity being the velocity of like the envelope, the outline of the entire wave packet as a whole, as opposed to the phase velocity of like each individual frequency component.
So it's like just another way to do the whole calculation, essentially.
Yeah, but to be transparent, quite a bit of this is over my head in terms of like what they're actually utilizing in these calculations. I can understand on a macro scale, like with the diagrams, what they're doing, but I'm not really getting the math other than in a very generalistic sense.
Oh yeah, I'm not crunching these numbers in my head, that's for sure.
Oh, you didn't do your second derivative with respect to the other one?
But I just think in theory, it's definitely really intriguing, in my opinion. I would be curious to, see it put to the test a bit.
It's cool how they got this diagram showing how they're wrapping and forming the light using lenses and spiral modulators, basically.
I'm glad you brought us back to that Mord one. That really was kind of the standout sentence of the whole paper.
Thanks. Yeah, I mean, it's kind of key to the whole enterprise, right? Because like it seems like this would be I don't really know the Maxwell equations all that well, but yeah.
Oh, dude, we're about to get real familiar with them, boys.
Nice. Yeah, should we move on?
No. Keep going until you're good on this. I gotta go to the bathroom real quick. So take a minute.
Cool. Well, I mean, yeah, if it's a relative jump off, then I'm ready. But we can give it a second.
It's interesting to me though that first. So if you look at that left side, it says, "Oh, yep, right, yep, okay." The here we exploit conformal mapping to reshape a photonic vortex tube into a toroidal vortex. See, they have a vortex tube, right? They have like the little cylinder tube where there's like a spiral going through it, and they wrap the ends around, make it a closed loop, and turn it into a donut. But it's still kind of interesting to me how they're doing that looking at the figure 3 diagram, because that first transform, the very first cylindrical lens and very first SLM1 module makes sense because that's turning it into the yeah, right there. SLM1 and cylindrical lens 1. That makes sense because that's getting you your little vortex tube or whatever. But at lens 2 and 3, it's interesting. Like I'm wondering. Oh, I guess it shows right there, elongated STOV. Okay, so that's what it looks like after it passes through 2 and 3, and then the SLM 2 and 3 are doing the spiraling and like stitching the ends together.
It should be interesting to know more about those SLMs, man.
Yeah. Am I wrong in thinking that in some sense, like, can we go to the where it's like curling? I guess the kind of diagram of. See, that looks like kind of simulation. That's cool. Yeah. Yeah. What's happening here? So it's like, maybe it's like, is the chirping like what creates this vertical beam, and then it's like a series of propagations through the lenses that curve it, I guess.
Oh, no. The chirping is talking about how like the fiber laser itself, the pulse that comes out of it has various frequency components that disperse at different rates. That's more with respect to the reference pulse. That's not what's causing this wrapping. This wrapping is being done by the SLM modules.
Got it.
Yeah, they get it into this tube shape, and then they use these SLM modules to bend it at a specific rate so that it wraps fully back around and reconnects to itself and makes the donut.
Yeah, the de-chirping is compensating for the inadequately built switching in the electronics end of the laser.
Interesting. Okay. Did they say what they generated these figures from? It kind of looks like ComSol or something, but I don't
No
really
idea.
know.
I don't believe they did.
Maybe if you go into that nitty-gritty stuff, I don't know.
Yeah, material.
Statements of data and code availability are available at that link, and all this other stuff. Source data,
Oh, I never
extended
did.
data.
I never did paste that for you. My bad.
Oh, no worries.
It is very interesting that they have, created artificially a toroidal light vortex ring, though.
Have you guys? Oh, this is kind of off topic. Do you mind if I kind of go off on tangent? I just thought of this.
I think we got a second. No problem.
Have you guys seen how dolphins use these toroidal vortexes to hunt and stuff?
Here's the supplementary information if you guys want it. I'll drop the link right here. Not to hunt. I know that they use the bubbles. They can like play with them and shoot them around like a kid playing with a ball.
Yeah, I think they yeah, it's pretty cool that they can like generate those patterns. So I guess in theory it would be the same kind of principle, right? That's what they're saying.
Here we find a picture taken online, available taken by Kelly Greco at Orlando SeaWorld, showing a dolphin playing with the toroidal vortex to help readers make analogy with the photonic toroidal vortex. Oh, here's the dolphin.
Cool. Oh, okay. This supplemental information has the it looks like it has the derivation that we were talking about.
Nice.
Yeah,
But it's
this has a lot more. Okay.
Yeah, it's a fucking bear though.
Yeah, yeah, it is.
Lots of math.
Chain, yeah.
Two-dimensional pulse shaper and spatiotemporal vortex. Yeah, I mean it's traveling along the z-axis, and it's traveling along the z-axis, and they're shaping it in the x and y-axis, I guess, or whatever, the tau axis, however they have it labeled. Grading, cylindrical lens, SLM, cylindrical lens grading. I see. Schematic of a two-dimensional pulse shaper. Oh, wow. Yeah, this has got a lot more stuff in it. It's got some really cool. It's also got some more cool images as well, actually.
I see that, yeah, and it looks like. Correct me if I'm wrong, but if you look at so they've got like a kind of like almost like a Snell's law kind of diagram. But if you look at figure S5, the characterization of the photonic toroidal vortex.
Yeah, that's what I was talking about. Yeah.
Yeah. And then, it showed the laser, and then phase measurement of photonic. Okay.
Because the pulse time on the reference pulse is so much smaller than that of the toroid, then they can break it up into like a whole bunch of slices and measure.
Yeah, I see that.
Interference at each slice. Because they're talking about like, femtoseconds versus picoseconds.
That's wild to even think about measuring something that quick.
Yeah, I know, right?
Oh yeah, guys, it's no big deal. The real and imaginary parts satisfy the Laplacian equations, and substituting into the Cauchy-Riemann equations, one finds a equation that's like fucking 12 terms long. No
Easy
big deal.
peasy.
Well, as long as your Laplacians are in order, you're good to go.
Yeah, don't get it twisted. I think a lot of this is like they're definitely using, computing to assist with, with this. I don't know that one of them just did all this in their math notebook one day.
They were using their abacus or whatever. Abacus.
So I think what they're saying with the approximation piece is that they have a numerical solution that's approximate to the Maxwell equations, and that's what they're running through. But
but what does that mean? Solution to the equations? Like, what does that mean? I don't even know what that statement's supposed to mean.
Yeah, so like any group of partial differential equations, evolution under certain conditions. And usually you have to make some simplifying assumptions. I'm not familiar with the maxwell.
Gotta do a little linearization game.
Yeah, something like that.
But when it says solution to the equations, like are the equations unsolved? Like, what does that mean? You know what I'm saying? Like, I don't understand.
Yeah, no, that's a good question. It would basically mean that like the equations are going to have like, so if we find like the actual Maxwell equations, right? Because I don't remember them off the top of my head, but basically it forms a system of 4 partial differential equations, like vector calculus differential equations. No big deal. But basically, in general, they don't have a solution generally. Yeah, there you go, Alan. But under certain conditions, you can solve for so for instance, here you have the variables are E, B, and J, right? I might be just totally fucking this up. But basically, you can solve for those in relation to their derivatives, but only under certain conditions, because the way that the partial derivatives work. And what that basically gives you is a set of variables that solve the equation that describes something about the propagation of the electromagnetic phenomenon in question. So I think what they're saying here is it's not like a closed form solution, like with the 3-body problem or whatever, but like kind of a similar thing. Like, it doesn't admit an exact solution, but you can approximate it. I think that's what they're saying, but I'm kind of speculating.
You think they're saying that electromagnetism propagates through toroidal vortex rings?
Well, what they're saying is it's kind of like basically it would be like a solution to the equations, and any solution to the equations describes a property of an electromagnetic field through some sort of medium.
Well, they didn't invoke a medium at all here, but they just said propagate.
I don't think you're drawing a line between coherent and incoherent light in terms of the geometry. I don't see the parallel.
Yeah, well, I certainly don't know what that means.
I think it's just to illustrate the math, essentially, I guess.
Yeah.
Interestingly.
Is this this 7.3.3 Maxwell equations, that last one, Ampere's law with Maxwell's correction? Is this before Heaviside changed it? You know what I'm talking about? IML Descu was like talking about like.
Yeah, I'm pretty sure this is after. Yeah.
After, okay. Yeah, the original Maxwell equations are actually different from the ones that are widely used today. They made a shorthand version of it and removed some of the original components of the equations.
The equations before Maxwell are on there as well.
Yeah, I see that.
Is Ampere that did that, right?
No, I can't recall.
I don't remember either. But yeah.
Thanks for hosting this. This was really cool.
Thanks for being here, man. Thanks for contributing. I'm really glad we were able to chat about that. It's cool. And hopefully we'll keep going here, because it seems like these papers really kind of segue into each other really well.
Yeah, definitely.
Yeah,
well, have a good night, guys.
Later, G. Yeah, we're about to get Maxwelled up. All right, so
I'm gonna have to tag out.
Later, G.
Yeah, later, Piezo. Thanks for hanging out.
See you later, man.
No worries, dog.
Cool. Well, you've got your notes in one pane.
Oh, right. Sorry, I was getting the thing for him.
Cool.
Ooh, what is this?
This is what we're reading now.
Yeah, so I've been talking about how Einstein, that they say that special relativity was the fix for restoring Galilean invariance for Maxwell's equations. And, they do that by the time coordinate, right? Like, that's the big thing, essentially, right? So anyway, Hertz did the same thing, but they just, only teach it through the lens of relativity being the correct way to do it. But anyway, this dude did a whole thing on it. And this paper is excellent because it goes over not only the history of that, but it goes over the difference between invariance and covariance, which mainstream mixes up a lot. And invariance is supposed to be like the representative of nature. The symmetry of invariance is supposed to, like, you know, represent the physical laws of nature, right? And then covariance is where variables change in a predictable way to basically conform to the invariance, right? So they use covariance to supplement invariance. And now in mainstream, what they've done is, like, everything is viewed through the lens of covariance. Like they just try to establish successful transformations for the things that they will change, or that they, like, will agree will change or whatever, to make the invariance fit. And the invariance being the speed of light, primarily through, you know, general and special relativity. When they get into that stuff with the contraction mechanisms, like, all of that stuff is covariance to make the speed of light invariant. So to kind of give the distinction there between the two. But as we go through, we'll, you know, that'll be covered. But yeah, it's a really good paper. So anyway,
invariant under transformation, right?
Yes, under specific transformation.
Yeah.
So,
got it.
All right. So Hertz's invariant form of Maxwell's equation by Thomas Phipps Jr. Abstract. The failure of Maxwell's equation to exhibit invariance under Galilean transformation was corrected by Hertz through a simple but today largely forgotten mathematical trick. This involves substituting the total time derivatives for partial time derivatives wherever the latter appear in Maxwell's equations. By this, Hertz derived a formally Galilean invariant covering theory of Maxwell's vacuum electrodynamics, which, however, was not space-time symmetrical in his view of tampering with time, but not the space derivatives. So Lorentz symmetry being adherent to time and space changing, right? So time dilation, link contraction. So the symmetry there is violated because you just changed the time, apparently, and was able to solve that. But there was an additional component that he found, which was a velocity component. And as I was reading this, I was thinking, like, oh yeah, ether velocity, or, you know, like ether wind, but it's actually different in the way that it works out mathematically, and it's really cool. So anyway, we'll keep going here. So had Hertz's mathematical accomplishment received wider recognition, his invariant covering Maxwell's theory could have furnished a formal key to the unification of the relativistic properties of electrodynamics, Newtonian mechanics, and the explanation of the Michelson-Morley result, etc. The task of finding a viable physical interpretation of the Hertzian convective velocity parameter, which Hertz himself did not live to accomplish, remains for continuing research. We will discuss this here in the related matters given to the explicit proof of the invariance. So he goes through and does some transformations to show that what Hertz was putting forward was mathematically viable. So introduction. There is considerable confusion in the literature about invariance and covariance of the equations of electromagnetism. For example, a paper by Jammer and Stachel states that if one drops the Faraday induction term from Maxwell's equations, they become exactly Galilean invariant. We shall demonstrate here on the contrary that 1, it is not necessary to drop the Faraday induction term or any other of Maxwell's vacuum electrodynamics in order to achieve the Galilean invariance, provided one exploits the mathematical theme due to Hertz. 2, if one does drop the Faraday induction term in the manner that Jammer and Stachel suggest, the resulting equation exhibits not exactly Galilean invariant, but might be more properly termed Galilean covariant. For another example, Miller, in an otherwise valuable review of Hertz's contribution, states his axiomatic assertion that the form of invariance of the electric field equations, or covariance as Minkowski described them as a mathematical property, led Hertz to predict new effects whose empirical confirmation would turn to serve to confirm his axiom of covariance. On the contrary, Hertz asserted invariance meant what he said. He was referring, of course, to Galilean invariance, since the Galilean transformation was the only one envisioned in his day. It is the Galilean invariance of the Hertz equation that will be demonstrated in this present paper. The modern word usage reflects received view of covariance are just as good as the form for invariance. To dispute this universal opinion appears fruitless, but it is completely confusing to represent invariance as an equivalent form of covariance. For invariance is what covariance simulates, emulates, or aspires to be. There exists a true invariance distinct from covariance, and the distinction is not merely formal. We shall presently show, in the case of electromagnetism, that physics of true invariance is as different from that of covariance as the mathematics. The writer has never encountered formal definitions of invariance and covariance that satisfy all the requirements of mathematical rigor, and none will be attempted here. Loosely invariant quantities in place of within the expression containing them without altering the mathematical character in any way. Covariant quantities transformed by a rule of generally linear combinations of related quantities, the rule being for the same for all quantities within the expression containing them. Right, so with link contraction, time dilation, as long as those change proportional to each other, it's okay, because those are just dimensional axes of the system. So the change there is expected, right? Like they're good with that. But something like the conservation laws for energy and momentum, or the speed of light, that has to be the same. So time and reality can can covariantly bend around those invariances, but and they take that bending and warping of the math. They're like, oh, look, that must mean we're super correct because of how we're conflating covariance with invariance. This distinction is best shown by example, which he does some great examples as we read on. Since the reader is undoubtedly familiar with the relativistic covariance, we will illustrate here only invariance to show the difference. So I was kind of already touching on the time and space coordinates being the change factor for relativity. So we're all pretty much up to code on that. So 2, historical brief. Let us begin with an overview of the situation on electromagnetism toward the end of the 19th century. A dominant figure, in addition to Maxwell, was Hendrik Rudolf Hertz, a physicist nowadays chiefly remembered for his experimental validation of Maxwell's theoretical prediction of electromagnetic waves. What is less widely recognized, but amply documented in his book, is Hertz's strength as a theorist. In the last chapter of his book, which appeared in 1892, he treated the electrodynamics of moving bodies by an original set of equations comprising of what we would call today an invariant covering theory of Maxwell's vacuum electrodynamics. The new equations differ from Maxwell's through the inclusion of an extra velocity dimension parameter in the components which Hertz designated alpha, beta, and gamma. The presence of this extra velocity parameter spoiled space-time symmetry of Maxwell's equations and caused them to become rigorously invariant under Galilean transformation. So, ruined the space-time symmetry of the equations, but was able to make them invariant with motion. So, very important in the hierarchy of mathematical logic and putting forward a theory as a proof of something, then backing it up with math. 1 second, got to reset the sand crabs. All right. Let's see. The extra presence of the velocity. Yeah, okay. We shall supply this in the next section. All right. Unfortunately, obscured in the new formulation of electrodynamics, such a baffling notion, all equations being written in the components unsimplified by the vector notation and identities. So all those nice vector notations and identities that we were reading about in the Chandos-Sakar book, I think it was, on physics, when we were learning about the kinematics and stuff, how they write everything all nice and neat. Well, I guess they didn't do that back in the day, and that makes this extremely difficult to read and understand for everyone. Is what he's saying. So it is a fair point to say that the physicists or scholars from then and now have penetrated it. So no one's really looking into it because it's just too many lines of code. Indeed, it is clear from Einstein's reference to Maxwell-Hertz equations in his 1905 paper that he was unaware of the importance of Hertz's invariant mathematics, insomuch as Maxwell's equations are space-time symmetrical, whereas Hertz's are not. We may conclude this summary by explaining why Hertz's invariant covering theory never got into the textbooks. His theory did not become physics because physics is never equations alone, but equations plus physical interpretation. As often as not, it is certainly the case that the interpretation proves to be the stumbling block. On the side of the interpretation, Hertz made a fatally bad guess. A modern mind would recognize the discovery of the Galilean invariant formulation of electromagnetism implies a Galilean motion relativity principle for electromagnetism as well as for mechanics, and thus automatically accounts for the Michelson-Morley outcome and corresponding to the first-order observations of Macquart and others, all of which shows showed relativity to be an experimental fact. Through formal attribution... Someone fix that. Thank you. Let's see where we're at. Through formal thoughts of the attributes of mathematics alone, without need of postulates of any physical ether in some collective state of motion. But Maxwell, Hertz, and most other late 19th century physicists were fixated on the ether. So when Hertz saw that there was a new velocity parameter unavoidably emerging from his invariant mathematics, he automatically identified it as ether velocity. See, I was thinking ether win too, boys. But in fact, he went one fateful step further in identifying his ether as with the converted ether of George Stokes. Oh yeah, he merged his idea or that velocity with Stokes's concept of an ether as well. So yeah, he was literally all in on the ether velocity as a wind for that to fix it. So anyway, such an ether, it was hypothesized to carry along 100% convected by all material bodies. By this merciless reckoning of the double-jointed hypothesis, Hertz's ether velocity component became the velocity of just any body in the laboratory, whence, in his last chapter title, perhaps unconsciously borrowed by Einstein, still referring to the electrodynamics of moving bodies. Dude, there's no way Einstein would have copied all that and used the same gamma factor or coordinate system stuff. There's no way. Total coincidence. One speculates that Hertz indulged on the dreadful definitiveness of the physical model because he distrusted the intangibles and wanted to include only measurable quantities in his theory. By boldly abandoning the ghostly quantities of the 19th century ether that protected it from empirical inquiry and making quote-unquote ether velocity operationally definable, Hertz's mathematics plus his Stokesian interpretation exposed themselves to the crucial laboratory testing. For example, they predicted that a dielectric rotating in the laboratory would produce a magnetic field. This effect was looked for soon after Hertz's untimely death and was not found. Hence Hertz's invariance was discarded and forgotten in favor of Einstein-Minkowski covariance. The covariant lads. Note, however, that it was not Hertz's mathematics that was empirically discredited, but the combination of that and obviously the unsound physical interpretation. An identical interpretational mistake was made by Maxwell, right? Because Maxwell was an ether lad too, right? He was like, "What are these lines of force doing?" or whatever. So, let's see. History, ever the Joker, forgave Maxwell's errant physics and preserved, indeed virtually sanctified his mathematics, the non-invariant special case of Hertz's equations, hence the formal term of comparatively degraded breed of mathematics. Said Hertz himself, intending a put-down that can only be read now as supreme historical irony. Maxwell's theory is Maxwell's equations, for history did not show the same courtesy to Hertz. Nobody had inspired charity to say Hertz's theory was Hertz's equations. Or Hertz's theory is Hertz's equations. This invariant mathematical baby was ruthlessly thrown out with the ether interpretational bathwater. Today, we would possess no electromagnetic theory whatsoever if the fairness of the doctrine had an equal degree was treated with to Maxwell as well. Right, the same thing they did to Hertz. Electromagnetic theory was developed by Maxwell's followers, proved to be tougher and less frangible than Hertz's theory, precisely because they were persistently vague about the physical interpretation side. Maxwell's luminiferous ether faded like a Cheshire cat's smile and was replaced by physically nothing, the most infrangible substance known, with the possible exception of the mathematical vectors and material for which the present writer was taught that electric and magnetic fields are fabricated. So yeah, when they're like, oh yeah, there's nothing there but a field of math vectors, dude, shout out to the boys. They got rid of the physical interpretation of it and then just, abstracted it to infinity. There is little doubt that Hertz deliberately sought after a frangible theory because he knew that that the breaking of theories in science progresses most rapidly. Right? The post-Maxwellians avoided frangible theory, perhaps one speculates because the goal of most rapid scientific progress was even in that day beginning to be supplanted by other objectives. Although Hertz's invariant equations went down the drain when they depend on certain immutable mathematical facts and thus are subject to continual rediscovery. The modern independent rediscoverer includes Kakowski, Tome, McCanoe, and the present writer, all originally ignorant of Hertz's priority. The mathematical facts will be examined in the next section. Hertz's electromagnetism proof of the first order invariance, considering the vacuum environments so that the constitutive relations do not enter, and choosing arbitrarily to designate the field vectors E and B, we can write Hertz's equations in Gaussian units in the form of 1A, 1B, and 1C. So we have the strength density of the electric and magnetic field and the relationship therein, right? Essentially what all these bad boys do. So where all the symbols have the same meaning, except will be discussed presently as the Maxwell-Lorentz equations. Actually, Lorentz's equations are more general in that they allow for a non-zero divergence of the B field, but we are more here concerned with communicating the ideas than historical accuracy. The total time derivative appearing in these equations is defined by equation 2, with d over t equals the derivative over the derivative for t, et cetera, right? So where Vd is the velocity dimensional vector, which represents Hertz's alpha, beta, gamma for that, whose physical interpretation was a crucial issue since it was because it's what tripped up Hertz and will be addressed below. It is obvious that Hertz's equations constitute a formal covering of Maxwell's equations for vacuum electrodynamics. For in the special case of the velocity parameter that assumes the value of 0, we assume the form of equation 2 that the total derivative operator d with respect to dt reduces to the partial operator d with respect to dt, with the result of equation 1, and it becomes identical to Maxwell's equations. In that special case alone does the space-time symmetry in a purely mathematical terms obtain symmetry. The measured current source of the term J in equation 1a differs by the effect of Galilean transformation from the current to the source J in Maxwell's equations, but the difference also goes to 0 in the special case as mentioned, and J would be the current density produced by the electric field, I think. When the new VD parameter does not vanish, the resulting, so that velocity parameter does not vanish, it remains to show that the case that we are dealing with invariant covering theory. We are dealing with an invariant covering theory. Since the present section is limited to considerations of the first order in V over C, the relevant coordinate transformation of the Galilean one is given by equation 3, where we adopt the velocity sign convection opposite of that of Jammer and Stachel. As noted by Jammer and Stachel, equation 3 implies, implies that where primed and unprimed quantities refer to two inertial systems in uniform relative station or translatory motion. So there's our equation 4 there. So observe that the velocity parameters in V, the inertial frame transformation velocity, and the VD convection velocity have nothing necessarily to do with each other, and both differ in general form any velocity parameter implicit of the source current density J. These distinctions being borne in mind, we need not concern ourselves with the pre-physical stage of the operation ally defining these parameters. Or operation, wow, I butchered that. Operationally defining these parameters. All right, we borrow from Jammer and Stachel the Galilean source transformation equations given by equation 5 and equation 6, which are certainly valid to the first order. We do not borrow the field vector transformation given by equation 7. Proposed by them. The first of these satisfactorily connotes Galilean invariance, but the second involves a scrambling of the linear combination of the electric and magnetic field quantities uniquely characteristic of covariance, hence properly termed Galilean covariance. For consistency with the requirement of true invariance, we demand that with the Hertz equation that the electric field that equation 8 be that the E field be equal and the B field be equal, right? If they're going to be the same under transformation, that they have to be equal. They can't mix match them. So the significance in equation 8 will emerge from inquiry to its physical meaning, which was postponed to section 5. For the moment, we simply take equation 8 as a formal ANSAT and examine its consequences. Regardless of what physical object or quantity VD refers to, it must obey at first order Galilean velocity composition law. So it has to obey Galilean velocity addition. Let's see. So given by equation 9, as we take note of Galilean velocity reciprocity, so velocity subtraction.
It's almost Sesame Street, velocity reciprocity. That's cool, man.
Velocity reciprocity. Although it will not be featured in our invariance proof, suppose we multiply equation 9 by the charge density P and arbitrarily define the formal current density JD by equation 9, where the minus sign has been introduced for reasons to be discussed presently. The JD transforms as this equation here, or given by the one in equation 12. We further define the measured current density, Jm, the quantity appearing in equation 1a, as the sum of equation 13. These are treated as a formal definitions of the source terms for purpose of the proof. They will be justified presently in the physical term. Finally, we assume the invariance of the ratios of equation 14, which is C prime is equal to C. All ingredients of the invariance proof are now assembled. We will show the invariance of the total derivative operator, given by equation 15. What a beast of an equation. Let's see, which follows directly from equations 2, 4, and 9. Next, we establish invariance of the measured current density given by equation 16, as it follows from equations 6, 12, and 13. With the following preparations, it becomes a mere matter of inspection to verify the invariance of the field equations themselves. The simplest equation, 1c, which yields equation 17 to show the invariance for the transformation, uses being made of equations 4, 8, and this agrees with equation 1c prime of Jammer and Stachel. By equations 4, 5, and 8, we verify the invariance of equation 1d. This agrees with equation 1a prime from Jammer and Stachel. Using equations 4, 8, and 15, we establish the invariance of 1b, given by equation 19, to show that transformation. So finally, application of equation A1 of equations 4, 8, 14, 15, 16 yields similarly equation 20 to show the full transformation. Thus, the Galilean invariance of all 4 Hertz's field equations, equation 1 in conformity with the ansat of equation 8, is established. There is no need to drop the Faraday induction term or any other. When, as above, each symbol appearing in a physical equation, here counting d over t as one symbol, the transformation directly into its primed counterpart. We may call this property of the equation manifest invariance, so we are entitled to speak of Hertz's equations as manifestly invariant at first order. This means that they obey Galilean relativity principle. The laws of electromagnetism, like those of Newtonian mechanics, are invariant under transformation among different inertial systems in uniform relative translator motion without rotation. Very nice. So the physical interpretation of the parameter VD. So is it the old ether wind or what? Because that's what I was rooting for, to be honest with you, but it turned out to be something just as cool, but not ether wind related. So to possess the formally attractive physical equation, it is not to possess a physics. It's not to possess a physics, as Hertz's experience confirmed. Generally, the hard part is to find a physical interpretation of the scheme or appropriate set of operational definitions. This is one of the bona fide physics problems that can never be delegated to mathematics. Now we address, with reference in this section to the Hertzian convective velocity parameter VD in the following section in our what did I do there? Section in our field invariance ansat of equation 8. Anasats, sorry. To draw inspiration from the master of physics of the past, we ask how Maxwell might have argued concerning the physical interpretation of Hertz's velocity parameter. I speculate he might have addressed the question from the standpoint of the equation of continuity, for this was never far from his thoughts, since it played a central role in his great quote-unquote discovery of the old displacement current. that led to one of the most dramatic predictions in the history of science, the existence of electromagnetic radiation, making the total derivative substitution for the mathematical consistency with equation 1 in continuity equation and applying the equations 4, 5, 15, and 16. Mike's going off, somebody. One second. I think you got it. All right. Let's see. There is nothing to be obtruse or even specifically electromagnetic about equation 21. It applies in hydrodynamics, acoustics, and in a number of familiar areas of physical study. In all cases, the meaning of the velocity parameter Vd is the same if we think of small detection volumes moving within a sort of generic flow. Then Vd is not the relative velocity of this flow. It is the velocity of the detector with respect to the observer. Oops. The partial time derivative appearing in equation 2 describes the time changes within the detector or charge density measuring device when it is held at rest when the velocity is 0, and in the flow at the fixed point with respect to an observer in the convective part of Vd times nambla of the partial time derivative operator describes the additional measurable or changes measurable within the detector specifically due to its motion, where Vd does not equal 0 with respect to the some inertial observer. So given such an interpretation, we can look back to our prior results and recognize the physical meaning of such a relationship as equation 11. The current density, JD, is part of the total current density, JM, measurable within the detector moving at a velocity, VD, with respect to the observer. And this is due to specifically due to the relative motion. It has a negative sign because the detector is moving in one direction and is equivalent to the current charges flowing in the opposite direction. Equation 13 states that the invariant of the total current Jm measured by the moving detector is the sum of Maxwell's source current J that would be observed if the detector were held stationary in our laboratory plus the motion generated by JD due to the proper motion of the detector with respect to our laboratory. Let's see. So in this connection, I believe Maxwell might have recognized that the detector's physical degree of freedom require parameterization in any theory compatible with the motional relativity principle. Those degrees of freedom were not parameterized. Thank you. It was getting me. I was getting myself on it. Anyway, parameterized in his own equations, since his field detectors were always tacitly frozen at rest at the field point fixed with respect to the observer. Given such recognition with regard to the to the charge density detector or rho parameter or rho meter, he would certainly have applied the same reasoning to the detectors of the field quantities, that is, the E meters and the B meters. All such meters can be considered instantaneously co-moving at the observer's field point, a stream of them being involved over time passing through the field point if the field point does not share their state of motion. All field detectors are compositions of matter having degrees of translatory freedom that need to be explicitly parameterized. If any motional relativity implies, or as motional relativity implies, the same formal mathematics to describe in more than one inertial system a unique event of detection occurring in one particular microscopic detector. 1 second.
Macroscopic, to be
Macroscopic. Thank you. What did I say? Microscopic?
Yeah.
Damn. Through such reasoning, one arrives at the operational definition of the Hertzian velocity parameter, quite different from Hertz's own. Whereas Hertz considered the velocity with respect to the observer of an intangible ether, rendering the tangible through the Stokes convective as bodies through or on the electrodynamics of moving bodies, as the assumption that we suggest that Maxwell or any comparable objective thinker might have been led to considerations as such as those were just not given to interpret Hertz's velocity parameter as the velocity with respect to the observer, not of any kind of flow, but of the tangible object, namely the field detector, radiation absorber, or instrument that measures the numbers corresponding to the E and B field component, the values described by the Hertzian field equations. I trust that the most fanatic of modern idealist formalists will allow the student the option to think of E and B fields in terms of the numbers, in terms of the instrument readings of the material instruments, in terms of the specific states of the motion of the object subject to parameterization, without co-signing them to perdition as discredited positivist. When VD equals 0, the field detector becomes just the Maxwellian detector at a fixed point. 1 second, I'm going to hit some water. Let's see. Where was I at? Yeah.
We're fixed at the field point.
Fixed at the field point. Thank you, sir. Hence, this fits exactly with Maxwell's equations, being the special case of Hertz's equations, where the field detector is at rest with the observer in the laboratory. In summary, it would appear that the most plausible interpretation of the Hertzian velocity parameter is that VD is the velocity of the field detector or the radiation absorber with respect to the observer. This has the advantage of designating the tangible object, and unlike the Hertz-Stokesian and ether interpretation, not being in conflict with observation, and has the minor disadvantage that no other rediscoverer of Hertz's invariant mathematics agrees with it. Oh, dang. So nobody else agrees with it, and that puts a big damper on it. It sucks. But probably for a poll of such rediscoverers would favor the ether interpretation, but an intangible ether not convected by material bodies, hence not subject to hostile interrogation under strong lights. 5. The contrasting physical invariance and covariance. It is expended to recognize that there is
expedient.
Thank you. At this point, it is expedient to recognize that there is nothing intrinsically right or wrong about the definition in mathematics or science, although there may be an overwhelmingly difference in fruitlessness, and that the Hertz's E and B fields are, by definition, different quantities from Maxwell's E and B fields. Hertz's field quantities are physically defined in a more general way via the measurements made by a detector that can move with respect to the observer and his chosen, quote, field point. As a result of this parametrically more complicated definition of the E and B fields, these field quantities acquire simple, manifestly invariant mathematical transformation properties under inertial motion. The Maxwell field quantities, by contrast, are physically defined, very simple, by readings of the field detectors permanently at rest in the observer's laboratory. As the result, they have more complicated transformation properties discovered by Lorentz and designated by Minkowski a few years later as covariance in contrast to invariance. Latterly, the terminological distinction between the two has been dropped by most physicists, but it remains mathematically significant and also physically significant as the present definitional considerations confirm. Dropping the distinction is not a general mere carelessness, but has serves as a propaganda trick to bolster covariance. What is the physics behind equation 8, which asserts true invariance of the Hertzian E and B fields? Simply that the observer is primed and unprimed in the inertial system, or indeed arbitrarily moving observers are in the same number of digital readouts of a given E meter or B meter at the instant it passes through the field point. If two or more different observers are involved, the field detection instrument in the equation in question can be at rest with respect to most of these observers, but the same instrument, the same readout, and the same numbers displayed on it are visible to all observers at the event of the instrument passage through the field point. The fact that all observers thus read the same field component numbers expressed by the equation 8, that the entire and entirely trivial physical meaning meaning of true mathematical invariance, right? So they all make the same reading, even though they're in different states of motion. The crucial point here to keep in mind is that the Hertzian electrodynamics or electromagnetism, only one E meter and one B meter is involved, no matter how many observers may be present. The instrument is public property. No one observer owns it, nor are the different observers called upon to replicate it. Replication of the experiments is not involved, and the states of the observer's motion are arbitrary and not necessarily inertial. The instrument itself, at least until more physics is known, must be considered at rest in an inertial system. Whether detector acceleration generates specific observable effects in question yet is not experimentally addressed as far as this writer knows. Covariance, by contrast, is subtler and conceptualizes physically in that we must picture as many instruments as there are inertial systems under consideration and must have both E and B meters present, say primed meters at rest in the prime system and unprimed at rest in the unprimed system, etc. Each observer reads only his own instrument and at the instant of passage through the agreed upon field point, and the linear combination of those numbers so recorded on the E and B meters by the unprimed observer must be calculated in order to predict the numbers recorded by the primed observers. For this, what do they call it? The Gedanken, for the thought experiment. For this thought experiment, operational complexity and necessity to introduce the calculational steps, in addition to the direct readings from the measuring instruments, it is quite clear why the operational definitions, despite a brave beginning by Einstein, is celebrated by Bridgman, have fallen into disuse by relativists in the Maxwell-Einstein electromagnetism. In Maxwell-Einstein electromagnetism, field detection instruments are private property and must be replicated by each observer. Thus, experiments must be replicated by different moving observers, and the observers must, in all cases, be inertial. As to the crucial question of the relative fruitfulness of the Hertzian and Maxwellian definitions of the field quantities that can be judged only within the context of the whole of physics, past and future. It might be a mistake to judge even from the present pinnacle of history of a pinnacle of historical enlightenment. In the era of Maxwell and Hertz, nothing was known that could have decided the issue between the two definitions, and nothing conclusive emerged from another quarter century, in fact, until the advent of quantum mechanics. The latter made it clear that the events occurring at the quantum level occurring at the macroscopic apparatus are physically unique, so that only a theory parameterized to describe the motions of a given unique macroscopic detector can work consistently at the quantum descriptive level. That is, the idea of the detailed, quote, replication of measurements within the macroscopic apparatus, and an idea that had served perfectly well all during the 19th century and well past 1905, and was finally played out in 1925 and could henceforth have nothing to do with physics as it has been refined, as its more refined levels of inquiry, or at its more refined levels. As indicated above, it is just this forbidden concept of replication that tacitly underlies Maxwell's definition of field quantities. For Maxwellian Einstein electromagnetism, each inertial observer has his own laboratory, his own fixed point, and his own field detector at rest at that field point. Lacking the descriptive Hertzian velocity dimension parameters that allow the field detectors to move with respect to the observers or the field points in each Maxwellian observer has to possess his own field detectors and is forced by the circumstances to replicate the observation of other observers, so that the micro sense of each measuring is a different field. Hence, no two Maxwell observers in relative motion can be talking about the same unique quantum detection event occurring in one particular piece of the apparatus. Einstein's relativity treatment applied to electromagnetic observations took over Maxwell's formulation unmodified, and hence, had Maxwell's replication been erratically built, built in. After 1925, the replication could no longer be legitimately applied to a single quantum event such as a photon absorber. Curiously, this was not observed by the noted investigators such as Bohr and Rosenfeld. A strange blindness seems to afflict the students of the field. Perhaps they are blinded by science. Perhaps. Who have learned the lesson of 1925 that the measurements cannot be replicated in the micro detail, and they cannot fail to recognize the invariance of the Hertzian definition of the field quantities, are better adapted to describing the physics of the quantum world. However, the aspects of Einstein's physics are certainly of permanent value. Throughout the course of the 20th century, empirical evidence such as CERN, muon observations have steadily accumulated, testifying to the correctness of Einstein's identification of the time-like invariant kinematics of the proper time interval. Therefore, it is evident that the Hertz equation can be at a best first-order approximation. If they have to have a physical validity at higher orders, their total time derivative d over dt with respect to the non-invariant Newtonian frame time appearing in equation 2 must be replaced by the total time derivatives with respect to the field detector's invariant proper time d over d tau d. Such a non-covariant introduction of Einstein's time-like invariant preserves at higher orders the vital mathematical invariance of the Hertzian equation, as well as their operational definitions in terms of the detector moving arbitrarily in the observer's laboratory. At the higher orders of Galilean transformation must be modified for the time coordinate, but they need not be modified for the spatial side, since the time-space symmetry has been jettisoned already at the first order. Similar remarks apply to the higher order modification of mechanics. Such considerations have been extensively treated elsewhere under the rubric neo-Hertzian electromagnetism. This is not detained us here. This need not detain us here, sorry. Despite the current vogue of covariance, Despite the current vogue for covariance, it would thus be premature to conclude as we approach the 21st century that true invariance is for all time discredited and played out. This seems a message of hope for the future of physics, for if there is anything that can sap the vitality of science, it is the total lack of controversy or intellectual challenge within its foundations. All right. So then he goes on to give a little commentary there, but I'm pretty tapped out. So that's pretty much it, though.
I got you covered there. Want me to hit the end?
Yeah, if you don't mind, if you would.
Sure, man. There has existed in the published literature for 100 years an invariant covering theory of Maxwell's electromagnetism due to Hertz. It should be emphasized that a covering theory really covers. That is, the empirically validated electromagnetic physics of one laboratory, wherein field detectors are at rest, is identical in Maxwell's and in Hertz's theories. By considering the equation of continuity within the framework of Hertz's formulation, we have been led to a view of the Hertzian velocity parameter quite different from Hertz's own interpretation. A different pathway to motional relativity thus opens up based on invariant rather than covariant mathematics of electromagnetism. On this new pathway, the E and B vectors transform invariantly because observers in all states of motion read the same numbers from the same instrument. The two types of field remain both formally and operationally distinct with no covariant scrambling of components. To be sure, there are many twists of the actual historical process we have not attempted to bring into our discussion. For instance, the Lorentz force law, which emerged contemporaneously with Hertz's theory, fits with covariance rather than invariance. But present-day empirical evidence is mounting heavily against the Lorentz force law and in favor of Ampere's original law of forces between current elements, refs 8 through 13, which honored Newton's third law, but not covariance or space-time symmetry. Hence, it may be premature to announce a final decision between those two similar-sounding, yet profoundly antithetical mathematical approaches to the description of an external reality, invariance and covariance. Today, almost all physicists consider the issue completely and permanently settled in favor of covariance. But we have seen that the uniqueness of the quantum detection event within a macroscopic piece of apparatus accords perfectly with the Hertzian one-instrument approach and not at all with Maxwell-Einstein replication of measurements in different inertial systems. The way covariance got its start was as best available substitute for true or manifest invariance, the latter being represented as unattainable because Maxwell's equations did not attain it. That was a misrepresentation of fact. So, in the addendum, a ref has made the comment, when the field vectors are truly invariant, are we not speaking of a Newtonian force field which could be made redundant by dropping the field altogether and return to Newton's simultaneous far actions? This would also remove all confusion regarding the ether. I concur with this thought and am personally partial to some Weber-type velocity-dependent potential that allows the entire purpose of the field to be accomplished directly by a simple intercharge force law. This fits much better with operationalism and with Occam than does field theory. The field, as an extraneous agent, is actually as objectionable, and for the same reason, as ether. It was not my intention in the present paper to defend electromagnetic field theory as physics merely to get it right on its own terms. We won't bother with the French.
Nope, I'm going to need you to read it in French.
L'occasion de Maxwell prouvé qu'elles sont des variantes dans les transformations Galilée et a été corrigée par Hertz grâce. No, we'll just leave this out, guys.
Nice.
Looking good.
Cool. Well, yeah, thanks for reading, Alan, and thanks for wrapping it up there, Stone.
Yeah, much appreciated. I was all out of steam.
It's like my second or third time looking at that paper, and definitely keep learning a lot more every time I look at it.
Yeah, it's one of those where you just keep passing it and you're like, oh, look, there's another thing I didn't know before, but now it makes sense.
Yeah. Yeah, I don't know if I've read that commentary at the end there before, but like literally the very last addendum there was really interesting. Like, oh well, Occam's razor would lean to an ether, yeah, but let's we're not talking about that right now. But cool, yeah. Well, does anyone else have any final thoughts or questions about the papers that we read tonight, or anything else regarding reading, research, whatever? Cool.
I did enjoy how he just dropped it all at the end and said, hey, why don't we just go back to Newtonian mechanics? Things were nice then.
Why don't we just go back to that or whatever? Yo, I see Cass over there. Did you have anything you wanted to add, Cass? I know this is something that you wrote about or written about. That's actually, I learned about this from you.
Yeah, can you hear me?
Yes, sir.
Quite well.
Yeah, I just joined a few minutes ago. I'm glad that Alan has taken up my suggestion to look into Thomas Phipps Jr.'s work. He's a very credible mathematician who has worked in an area I would call applied math. That is, applied the mathematical principles that he learned to scientific issues. And one of the most important things that I noted, I don't know if you covered it in the talk, because I don't remember this paper in detail, but one of his most important contributions was to show that the Maxwell equations, if you add ether into them as the basic substrate on which all physical interactions take place. If you add that, you can show that Maxwell equations are Galilean invariant. And of course, without the ether, Maxwell's equations are Lorentz invariant. So when Einstein proposed his special relativity theory in 1905, then there was a decision that had to be made. Well, we know that Newton's laws are Galilean invariant, and without ether, Maxwell equations are Lorentz invariant. But if you add ether, which makes them, I think they're called the Maxwell-Hertz equations then, because Hertz adds in the ether concept. So you have a conflict between Galilean invariant for Newton, or laws of mechanics, and a conflict with the Lorentz invariance of Maxwell. So what did they decide? You have this choice. They decided they would make Newton's laws Lorentz invariant, which means now we get the factor of the gamma square root function, and when you use the first approximation, you get all these v squared over c squared corrections to mechanics. And now you have both mechanics and electromagnetism. Now they're both Lorentz invariant, which is just the opposite of what the path that should have been taken, which is, all right, we've made the Maxwell equations Galilean invariant. At least Thomas Phipps has shown that that can be done. And that's what we should have then, is Galilean invariance as the basis for all transformations of either mass motion, which is mechanical, or the interactions of electric and magnetic fields, which is Maxwell's laws. So if we could get mainstream to go back and consider the wrong choice that was made, and consider that special relativity, first of all, it's flawed in its postulates. Both postulates are experimentally proven to be false. So to me, Phipps' contribution, and he made some other ones that maybe I'll put together a paper and point out what they were. His main contribution was to show that the proper transformation laws are Galilean transformations. And whenever I have then a theory that is based on Lorentz theories, I basically ignore them, because anything that's based on Lorentz transformations is inconsistent with what was proven by Phipps, and well, assuming that you include the ether as the fundamental interaction in electromagnetic fields. So as far as I'm concerned, that's what Phipps contributed. The invariance of all laws of physics, electromagnetism and mechanics, all are explained by the Galilean transformation. I don't know if that was brought out in the paper, the part that you read tonight, but for me, that's the important part of what Phipps has contributed. Okay, that's it.
No, thanks. Much appreciated. Yeah, he touched on it a little bit, not necessarily like mechanistically, but he was like, that velocity component is the key to, Galilean invariance. But he didn't like describe it or like, add any specifics to it other than just that it was the velocity term.
Yeah. He also is, he's also a leader in understanding what an inertial frame is. And that's also one of the things I would recommend that you consider in your reading history.
Will do. What is there a specific title on that? Do you have, or is it just part of his works? And I'll find it.
No, what I have is his 600-page book. I forget, it's called Verities, or
it's called Old Physics for New: A World Alternative to Einstein Relativity. Or no, wait, it's only 200 pages. You have the Heretics one?
That's what you just read was the paperback. He has 2 books.
Oh.
And the one that's almost impossible to get now is the one Heretical Verities, I think it's called.
Yep.
Heretical Truths. And that's worthwhile, I think, in making public. Maybe I could make copies of the relevant pages and pass them along to Alan, and then you can decide what you want to do with them. But is in my mind one of the 5 leading dissidents in the battle against mainstream physics, modern physics that we encounter today.
Yeah, dude, definitely send me those scans. Because I went looking for that book and I could not find it anywhere.
Yeah, I know I paid almost $100 for it.
Jeez.
And that was a few years ago. Because I couldn't get it in any other way. There's no Sci-Hub or any alternate way of getting it. And it's still, I have a paper copy, so I don't even have a PDF, which would be much better for distribution.
Well,
like I said, I'll try and make copies.
If we pay the shipping, you could send it to Toby. He could scan it and send it back to you, and then we could disseminate it from there. Because he has a special copier for all that, don't you, Toby? You still have that?
I do have a scanner. It's not super special, but I do have the ability to scan stuff in. Yeah.
Oh, I thought you had like a special one or whatever for the Einstein book you put out. But yeah.
Yeah, it's special because Toby put 30 hours of man labor into it.
Oh, dude, no way.
Yeah.
Okay. Yeah, so I just volunteered Toby to do that. Well, I also have a scanner too. So
smile and everything.
I thought you had to have a special one.
I would have no problem doing that if we can get. If that's the only way we can get it, then I'm down.
Yeah, it would only make sense to copy the pages that I think are relevant. And I do have a copy machine, but it's, you have to load each page, copy it.
Yeah, it's disgusting. No, I sympathize. That's why I pushed it off to Toby.
Yeah, what a good guy.
Yeah. Alan, you're the man. Huh?
Yeah. I was like, Toby will do it. He has a scanner.
If you do want to send it, I can scan it in. But yeah, we can scan in the pages you want or whatever. We can discuss.
Toby has a super scan. It only takes him 30 hours. Don't worry about it. It's super good.
Yeah.
He only has to do it page by page manually. It's fine.
Alan
how
loves to volunteer, right?
I
He
like how you
volunteers
automatically
Toby.
assume that
Yes,
Toby figured out a
Alan is
better.
Okay.
Alan is a masterful delegator.
Yes.
Like obviously Toby didn't do it manually, right? Because
So
Toby's Toby. He found a way that was above and beyond, and like coded.
so
Like,
that was
no,
my
nope,
rationale.
nope.
So let me go back to my justification for throwing Toby under the bus. Okay. The Ron Hatch book is really long, or a lot of pages. And Toby said that I could have sworn he said that he bought a new scanner or something just specifically for that. So in my mind, I'm like, oh, magic book scanner. It just automates the process.
It's slightly better than I mean, it's like not a printer scanner, it's a scanner alone, but it still is like scan every page one at a time.
Oh yeah, that's
Do the
super
back of the
gross.
page,
My
fold it over, do the
apologies.
next
My apologies for
page.
volunteering you for that. I thought you had a special scientifically advanced piece of technology that
You're all
automated it.
Well, it's funny, but honestly, like I would have no problem scanning this. And this is the more work from who we just read, right?
Yep.
Yeah, I'd be pretty down to scan that in. So, or if you have a scanner too, Bennett, however we want to do that, it doesn't matter to me. I can definitely ship it back. But yeah, it's the same situation because that was with the Hatch book. It was like $100 something bucks, super hard to find, and I was like, all right, let's at least get this digitized for myself. But yeah, so I think we should probably wrap things up here. We're going into
Yep,
2 hours.
absolutely. Absolutely. Let's close it
Or
down.
just 2 hours, never mind. But yeah, let's wrap it up. So thanks everyone for listening in. Again, thanks for bearing with us as we switched our schedule again. So we'll catch you guys all next Tuesday for a round table. It'll be either a discussion, open discussion, or maybe like a presentation. And then we'll see you next Thursday for more reading and research. And if you ever want to bring something to read, you ever want to bring something to watch, something to talk about, please come on in and do some reading and research with us. So yeah, good night everyone. Take care.